as Jean-Philippe said, I will present to you the work done during my PhD about mechanical consequences of femtosecond laser irradiation of metals. So I'm working at the École des Mines with András Bovedi, and here also at the Laboratoire Berkerien. So first I will introduce you to laser pinning, which is a technique already used in the industry, which consists in focusing a laser beam on the surface of the metal we want to process. And thanks to a sacrificial layer, the plasma is stayed on the surface and creates a pressure wave which propagates below the irradiated surface. And this propagation creates a local plastic deformation, which results in residual stresses remaining after the shock wave. So this allows to create some quite high pressure wave, about some gigapascals, and to impacts up to 1,000 microns. And the consequence is the improving of some mechanical properties of this metal, including hardness, fatigue resistance, or corrosion. And it's used in automotive and aerospatial industry. The specificity of this work is to reproduce this thing on with femtosecond lasers, because it has been shown by Seno that this technique didn't need any sacrificial layer, so which will allow other applications. Why it doesn't need any sacrificial layer? Because the origin of the shockwave is not the same. During femtosecond laser pinning, the laser only interacts with the electrons of the material, which creates a high disequilibration between the temperature, the electronic temperature, and the lattice temperature, which we can see here in the graph, and which creates the propagation of the wave, of the shock wave, without any sacrificial layer. So the difference, as I said, is that there's no need for a sacrificial layer, and it also produces a much higher intensity shock wave, up to dozens of GPa, and the impacted depth is smaller, around 100 microns or less, depending on the material, we'll see. And one advantage also is that the thermally affected zone is smaller than in nanosecond regime, so it destroys less the surface. And the consequences are the creation of microstructural defects, especially dislocations, and the improvement of the material, of the resistance to fatigue of the material. So for this work, we are working on three main axes. First, modeling and numerical simulations in order to understand the creation of the shockwave and how it propagates. And the second axis is experimental and includes characterization of pinned samples thanks to XRD techniques. And the third axis is the assessment of fatigue life with micromechanical tests on them. And the goal is to understand how the metals interacts with the lasers during the pinning. To do so, we are doing some comparison between materials, including aluminium, nickel, titanium, and iron, and the impact of the laser parameters on this pinning, which are fluence and pulse duration. So let me present the methodology with first the numerical simulations. So we are using a combined model of two temperature and molecular dynamics. So it consists in making two subsystems of the material, one for the electronic part and one for the atoms, the ions. So the first, so to simulate the laser on the material, we are using the two-temperature model, which creates a source from the gradient of the electronic temperatures, and which is linked to the other subsystem thanks to an equation of Newton's equation of motion to compute the movements of the atoms during the pinning. So to implement this, we need some parameters for the TTM model, which are the electronic specific heat, the electronic thermal conductivity, and the coupling factor between the electrons and the photons. And we also need a realistic potential, which is adapted to this use. And then we solve the equations with the Verlet algorithm, and we get as an output the atom position as a function of time and space. And we can compute the thermodynamic variables. Then let me present the methods for laser irradiation. So we're using pure metal samples, almost pure, and we prepare it by cutting and polishing in order not to have any residual stresses, which we check with some XRD measurements. And then we irradiate them thanks to a scanner in order to irradiate the whole surface of the material, playing with the parameters which are fluence and pulse durations. And then we do some control measurements, including ablation, depth, and surface roughness. After these irradiations, we are doing some XRD characterizations, including laboratory measurements in order to compute the residual stresses below the surface, and also some high-resolution peak measurements in order to calculate the dislocation density, and to be more precise than in the computation of the dislocation density gradient below the surface. We are also doing synchrotron measurements, which allow to focus a lot more the beam, the X-ray beam, and to get an accurate gradient with a 1 micron step. So let me present some results. First on the shockwave formation with the simulations, and then on the residual stresses and dislocation density evaluation. So here's nothing. Here's a picture of what we can get from the MD simulations, where you can see the laser is coming from the red arrow, and then we can see that with different time delays, some of the solid FCC atoms becomes liquid, and then when they become solid again, some stacking faults are remaining, meaning that there are creation of dislocations. And then we can compute also some pressure maps. Here they are all on aluminium, and for 4 different fluence, incident fluence values from 2 to 12 joule per centimeter square, we can see that the very high pressure shockwave is created, and that the values of this pressure under the surface is linear as a function of the incident fluence. These are results from the measurements I spoke about done at the SE synchrotron, where we can see the evaluation of the dislocation density below the surface, with the irradiated surface. What we can notice, and which is coherent with what we saw in the simulation results, is that when we increase the fluence here, just below the surface, we increase the dislocation density. This is true for the three first fluence here, And what we can see is that there is a different behavior at very high fluence. So in order to explain this difference, I have done some other characterization from those measurements. The first one is the residual stresses measurement. What you can notice here is that for the three first values, so which are those three first curves, the values are negative, meaning it's a compressive residual stress. And for the other one, the one with the different behavior, we can see that these residual stresses are positive. So this made us think that this could come from a recrystallization which occurs at the surface. And to confirm that, here's an EBSD map of the done just below the surface of the irradiated sample. So here is the irradiated surface, and you can see that there are some big grains everywhere here, and these are coming from recrystallization, because as I prepared the material, it should be like this, like, coming from the cold world. Now let's compare some values from different materials. Here is a graph showing the normalized interplanar space, so from XRD measurements, and it is shown as a function of the depth below the surface. The surface is at 0. And what we notice is that for nickel and aluminium, for iron and nickel, the values are way smaller. The penetration below the irradiated surface is way smaller than for the two other materials. So this could be linked to the electron phonon coupling factor, which is way higher for titanium and iron than for aluminium and nickel. And last thing I want to present to you is some XFEL measurements, which have been done 2 months ago. In order to compare more precisely to the simulations and the shockwave propagation, we have done a pump and probe experiment at XFEL, consisting in putting the optical laser on the edge of a sample, and by making it at the same time with the X-rays coming here from the other edge, we are able, by playing with the delay between the laser and the X-rays, to see the propagation, the variation of density below the surface, and so to get the propagation of the shock wave. So what we expect is to characterize the shock wave, its speed, its pressure, and the evolution of its propagation with the reconstruction as shown on these images, which are not images from this measurement, but that's what we expect to get. And also we are doing some diffraction analysis during the shock wave. So we expect to see the peak position moving and the shape of the peaks moving also, and to evaluate the creation of the dislocation density during the pinning. So here's a picture we get from the measurement. So here's the surface, here. And what you can see here, we have just put the laser on all time, and you can see that the surface starts moving and ablation occurs. And so for some, so here's a result we get. It's a preliminary result, it needs more post-processing, but here's the surface, here's the initial state, and what we get here, you can see that something is happening. So this could be the shock wave or a consequence of shock wave. So some forthcoming results on the road, let's say, and I hope we can say more about it in 6 months. Thanks for your attention.